Hello, everybody. Welcome to another edition of Cosmos from Your Couch, brought to you by the Dunlap Institute for Astronomy and Astrophysics at the University of Toronto. My name is Michael Reed, and I'm the Public Outreach Coordinator at the Dunlap Institute. And I'm here to bring you one of our talk series that we hope will help entertain and educate people while many of us are stuck at home on lockdowns and in quarantines, things like that. So today's guest is Emily Tyhurst, and Emily is going to be talking to you about tension in the expanding universe. This is a really fascinating issue, and I think you're really going to enjoy Emily's talk. So Emily is a doctoral candidate in the Department of Physics at the University of Toronto, and her research spans a bunch of really fantastic, amazing topics, everything from the very small with quantum computing to large-scale structure in the universe, which is the study of things on the biggest possible scales. But as I say, today she's going to talk to you about tension in the expanding universe. So please take it away, Emily.
Hi, everyone. Thanks for that lovely introduction, Michael. It's been actually a little bit since I've done any quantum computing, but definitely if you put my name into Google, some quantum computation stuff will come up, and I have a couple of papers that I worked on in quantum computation. But yes, as Michael said, I am a doctoral candidate at the University of Toronto. That basically means that I am a PhD student, but I have recently done my qualifying examinations. So if there's anyone in the audience who's thinking about someday going off to try and do their PhD, your qualifying exam is a test that you will pass wherein you'll propose your research to your committee and they'll give you an examination. So I recently moved past that, and I thought a great way to celebrate would be to do this talk about tension in the expanding universe. Now, the talk that I'm going to give you is actually not related to the research that I do, but I was inspired to give this talk because of discussions that happened on Friday between the cosmologists at the University of Toronto in the Canadian Institute for Theoretical Astrophysics, where I work. So in this talk, I'm going to tell you about something that I hear about on average every 2 weeks in these discussions, which is the Hubble tension. So let's get into it with a kind of general question, which is, there we go. What do you think of when you think of a scientist? What image comes to mind? A lot of people think of Albert Einstein. If you mention the word physics, some people think about writing equations on a blackboard, maybe some diagrams that you don't fully understand. Maybe you've even seen some of these diagrams in the background of an episode of Big Bang Theory. But when you think of a scientist, what kind of information do you think scientists can give us? So one misconception that I see a lot even now is that, scientists are brilliant geniuses who never get anything wrong. Every scientist is an Einstein, and everything in your textbook, everything in all the scientific literature, all scientists agree on. And sort of a corollary to this is the idea that a scientist who gets something wrong shouldn't have been a scientist in the first place. Scientists always get things right. And, if this sounds kind of silly to you, it's certainly because it is. If I had to get everything right all the time, I'd have to turn in my science card immediately. So if you're somebody who's thinking about going into science and you're worried about the fact that you struggle with the subject, many scientists before you have struggled with the subject, and that's part of the process as well. So the kind of other corollary to this misconception on science is if scientists can get things wrong, well, some people ask, why is it that we listen to scientists? Even Einstein is wrong, and often. And some people get the idea that scientists are always changing their theories. And that kind of leads into the cynicism that we don't really know anything about the world, and science stuff just obscures it. If you're tuning into this talk, I'm sure you don't think this about science, but it's something worth entertaining, that some people can go from this very high-minded view of how scientists work and then be very disillusioned by the idea that sometimes it's difficult to know exactly how things work, and we have to revise our ideas. Any good scientists will admit that they're wrong and revise their ideas. The question I want to focus on in this talk, and I want you to kind of ponder for a minute, is how do you think scientists disagree? And how do you think we find out whether somebody has got something wrong? So this is a graphic from UC Berkeley about a kind of passionate discussion happening in front of a blackboard, possibly between two physicists. And Another misconception is that scientists never get kind of excited or passionate about their theories being right. I can, assure you that scientists definitely do get very, attached to their given theories. So the overall picture I want you guys to have in mind as I'm going through this talk is of two different scientists, two different science groups who have a measurement they're making. So one scientist has come up with a carefully thought out experiment to test a theory or make a measurement or both of these things at once. And I've put down a number that you probably remember at some point learning from physics, which is G, the gravitational constant, 9.1 meters per second squared. So maybe over here, this person has measured the gravitational constant by dropping a bowling ball in their lab at the bottom of a valley. And over here, another scientist comes up with a different experiment. So maybe they're dropping their tennis ball at the top of a mountain. And we're getting two different values for what the gravitational constant is, subtly different values. So this disagreement between measurements leads to discussion and generates new science. So this is sort of a general picture of what a disagreement in science can lead to. Now I want to get into how this applies to the topic of this talk today, which is the Hubble tension. So let's take a step back right now, and I'm going to tell you what is the Hubble constant. So if you've been tuning into these talks, I'm sure you know the universe is expanding and expanding. Maybe that song is stuck in your head now. If you want to look up Monty Python's universe song, you should give that a shot. It's a really fun tune. I love it as a scientist. So the picture you want to have of the expanding universe is that of a balloon with dots drawn onto it. And the dots, which are galaxies or bright features we can see in the sky, are getting further and further away as the balloon is blown up with air. So the space between them is getting bigger. And the Hubble constant tells us how fast at present day this expansion is. So this image is from Emma Vanstone. You can, visit this link after the talk and maybe try this little analogy illustration experiment at home. If you want to learn more about the Big Bang, the first talk in the Cosmos from Your Couch series, Misconceptions about the Big Bang, goes into a lot more detail. I'm not going to linger on the details of the Big Bang in this talk, but I wanted to plug that if you're really interested in hearing more about the science of the Big Bang. So the picture I want you to focus on for the Hubble constant is we would like to measure how space is expanding. So say we had some feature like a group of stars, a galaxy, and say that we know the difference between these two things at a given time. And then later we measure that distance and it's gotten bigger. We can use that to determine how much the universe has expanded in that time. But the question of knowing a distance between things in the universe is actually a much, much harder question than it sounds. To illustrate this, just ask yourself, how do you think we know the distance from Earth to the sun? I'm sure at some point you've heard it's 150 million kilometers or 1 astronomical unit, but have you ever thought about how we got to do that measurement? I mean, I'll tell you very briefly, the ancient Greeks had a method for measuring it based on the phases of the moon, and more modern methods use the transit of Venus. And already these things are sounding, quite complicated, and they use other features in our solar system. And this is just to measure the sun, which, compared to a galaxy is really close by. So if you want to find a ruler that we know really well, and use it to measure the Hubble constant, you're going to have to be kind of clever about what it is that you're doing. So this leads us nicely into the first measurement, which is about the cosmic microwave background. So the cosmic microwave background is the first light from the Big Bang, the first light that we can see when the universe started. It happened at about 375,000 years after the start of the universe. And you might be asking yourself, why so late? That's 375,000 years that we couldn't see. Why can't we see anything before that? And the answer to that question is that everything at that time before that was really closely clumped up together. And the light, which is the information that we can see, wasn't able to escape in order to get to us. You can think of a Plinko game where the pegs that the ball is bouncing between and the ball is light, the pegs are just really, really tightly close together. And the ball just is stuck between a group of pegs and isn't actually going anywhere at all. But as the universe expands, the pegs are able to get further apart and the light is able to escape and flow towards us. The microwave part of the cosmic microwave background refers to the wavelength of light. So microwaves as in coming from your microwave oven, but microwaves, as distinguished from visible light or from radio waves. And even just the fact that we know, based on our theories, that the cosmic microwave background should be in the microwave regime tells us that we understand this cosmic microwave background pretty well. And indeed, what we get from the cosmic microwave background is essentially a balloon with some spots where we have an idea of the spot spacing. And then we use this spot spacing to determine the Hubble constant. If you want to learn more about the cosmic microwave background, which is an amazing cosmological observable, I'm again going to say you should give a listen to Misconceptions about the Big Bang, which really gives the full story of why the CMB is so interesting to us as cosmologists, as astrophysicists. But for now, I want to leave this with, we understand, spacing of dots on the cosmic microwave background, and this is what allows us to get a measurement of the Hubble constant. This is your first measurement in terms of two camps doing measurements of the Hubble constant. To move on to the second measurement, we're going to use some other reasoning to get ourselves a good ruler. So looking at this picture of streetlights by the highway, you see that the streetlight that's closest to us is very, very bright, and then a streetlight further away is dimmer and dimmer and dimmer. Now, if we know that a streetlight, they all have the same kind of light bulb, which is a pretty reasonable assumption, all things considered, we can say that the brightness of the light corresponds to how close the light is to us. So then, if you imagine a light that's moving away, we can measure how bright it is as it moves, as the universe expands, and then get a sense of how fast that distance is receding to us. This key point is we need to find a light bulb that we understand really well, rather than a distance that we understand really well. So one of these light bulbs that we're pretty confident we understand is a supernova, specifically a type 1a supernova. And we use this observation of a supernova to make a distance measurement in the same way as looking at lights on the highway. So taking a step back, what might you have heard about the Hubble tension? I pulled a couple of articles from some popular science and looking at these really interesting headlines. So more evidence that our model of the universe is broken. Hubble tension headache. Sometimes it feels like a headache when we're in these cosmology discussions. Clashing measurements make the universe's expansion a lingering mystery. And that's from Scientific American. And tension over Hubble constant continues from Sky and Telescope. For whatever it's worth, this one was my favorite article. So if you're looking to read more about the Hubble tension, I do recommend this article. And I show a figure from that article, which was taken from an actual scientific paper. So the take-home picture I want you guys to have is that we have one camp, the cosmic microwave background measurements camp, that says the Hubble constant, H0 is what scientists refer to as, is 67 kilometers per second megaparsec. The supernova camp is saying that it is 72. So is this actually a problem for scientists, that one group says it's 67 and one group says it's 72? At first you might be thinking, of course it's a problem. Those are two different numbers. But when physicists talk about two different numbers, we ask for a little bit more precision about how those numbers are known. So I'm going to take a moment here and tell you guys about this third image that was in my intro to my talk, which featured these little guys that look kind of like little satellites or UFOs. This is, satellites or UFOs were what I thought these little graphics looked like when I saw them in my first year of undergraduate physics. Just sort of as a side note, I made this graphic myself. I think it's kind of fun when science graphics are a little bit amateurish. So, a scientist made this is my feeling in looking at this. But let's take a look at these little UFO guys. So I'm going to tell you about what uncertainty is. So in order to talk about uncertainty, let's talk about a common question from the perspective of scientists. A common question is this glass half empty or half full? But what a scientist, what a physicist would ask you is, how sure are you that the glass is at half? How are you going to measure that sureness? What is the maximum that the glass could possibly be in height, or the minimum? So you take your ruler and you make a measurement of the height of the water, and you say, okay, well, from the bottom to here, it's about the same as from here to here. So it's definitely at half. The glass is at half. And when asked how sure, you say, well, I can only measure as precise as my ruler allows me to. So I'm going to say that it's half plus or minus the rounding error between 2 ticks on the ruler. So plus or minus 1/16 full. And if you want to make a more precise measurement, you've got to get yourself a better ruler than the one that I've shown in this picture. So, say we have the cosmic microwave background measurement saying that the Hubble constant is 67 plus or minus 4, and the supernova measurement saying the Hubble constant is 72 plus or minus 3. What does that look like on a graph? How would scientists see this information? So we've got this graph here of the Hubble constant, and I've put time on the bottom because it's an easy thing to put on the bottom of the graph. So we've got early universe measurements and more recent time. And 72 is the value that the supernova says it is. And these little arms here, the arms of the uncertainty bars, give us the total range of what are the values that the supernova could also plausibly say that the Hubble constant is. So that's a maximum of 76 and a minimum of 68. And to physicists, all these numbers are reasonably okay. They all could be what that measurement is saying that the Hubble constant is. Similarly, on the cosmic microwave background side, we have uncertainty bars that give us a value of a maximum of 70 and a minimum of 64. And we take these two things together and see there's this nice region of overlap. So if the uncertainties overlap, we don't actually have a problem at all. There's no problem whatsoever. It's just a matter of getting better rulers, and once the rulers get better, the measurements will agree. So now let's take a look at an actual graph from a scientific paper, the one that I mentioned earlier. So here in the year of publication, in the year 2000, we have a couple of different measurements of the Hubble constant. So Cepheids here are a type of star that varies over time, and it's a measurement very, very similar to the supernova measurement. So it's another light bulb in the universe that we think we understand. The tip of the red giant also uses, tip of the red giant branch also uses similar methods. And then CMB is the cosmic microwave background here. So, starting in 2000, things were great. The measurements of the Hubble constant had big uncertainty bars, but they both agreed. And, as time went on, we made better equipment, better measurements, and things started to, sneak away from each other. But no one thought this was a problem because the uncertainty bars were still within each other. And then, 2012, 2016, those uncertainty bars keep shrinking and the measurements keep getting further and further away. So this is what the Hubble tension looks like to a scientist. It's, not just that the values themselves are different, it's that our uncertainties for them say that they are not compatible with each other's measurements. So now what do? Well, an experiment by necessity will include assumptions. And I want to be very clear about that. Some people think that having assumptions means your experiment is wrong. You cannot make an experiment without some assumptions. And it's very, very important that you list your assumptions and you think about your assumptions so that if you run into problems, you can revise them and think about the physics that goes into them. A common question, if we go back to the glass half empty, glass half full, the assumption here, I have two observers who are observing the glass from above and the glass from below. And the assumption here is that the height of the water doesn't change, from above or viewed from below. And that sounds pretty reasonable, right? Like, why would the water change if you just looked at it differently? But as it turns out, if you're measuring it precisely enough, and you might remember this from chemistry in high school, if you're measuring the water precisely enough, the bending of the light as it reaches your eyes will cause you to measure differently from if you're looking above or if you're looking below. So in looking for that systematic error, you've actually learned something about physics. You learned about the way the physics of light reaches your eye. So this is what these two teams are doing right now. They're asking questions about systematic errors. They're asking questions about early universe physics in the cosmic microwave background case. And in the supernova case, asking questions about whether we understand supernovae. Do we really know that light bulb as well as we think we do? Both groups have questions about equipment, and estimating uncertainties based on equipment is a lot more complicated than just the ruler example I showed you there. It's a really, really interesting field of study. So, okay, let's take a step back from this talk. I've been talking right now this whole time as if this is this war between two camps, CMB versus supernova. One of these groups is going to be right and win, and the other one is just going to sort of contribute to science, but they won't be right, so it's not as important. And there's actually not, it's not just the two of them in the room here. There's also a third group that neither of them, that's independent from either of them. And this group is asking the question, what if it isn't systematics? What if the problem in the way we understand these measurements goes deeper than that, and we need to revise the way we think about the universe to see this Hubble constant? And I'm going to call this category new physics. Let me be clear. We, in our cosmology discussion, talking to other astrophysicists, we call this new physics. So, this is actually a technical term. Going back to that graph, you'll notice I put time on the bottom, and you could ask sort of naively, I mean, what if the Hubble constant changes over time? And that's a deeper question than it appears, because there's a reason we call it the Hubble constant in our current theory. But I'm going to take a step back from the graph, from the idea of the Hubble constant, and just talk for a little bit about the process of examining and accepting a new theory in science. So I'm going to use the example of classical mechanics, because a lot of people have heard about classical mechanics and know that quantum mechanics is kind of a new paradigm that we're using a lot. So in this case, classical mechanics has experiments that it explains really well. So something like a rolling bowling ball is really well described by classical mechanics. However, something like what an electron is doing, the behavior of an electron, not well described by classical mechanics. So this problem of making a new theory that describes both a bowling ball and an electron is solved by quantum mechanics. Quantum mechanics is good at doing the old stuff. You can definitely do those calculations with quantum mechanics, and it's good at the stuff that the other theory wasn't quite measuring up at. But more importantly than both of these things, quantum mechanics also makes new predictions. So for example, quantum mechanics tells us that the same behavior we see with an electron, that wave behavior, we should see that with buckyballs, which are large structures of carbon. So the success of quantum mechanics depends not only on its ability to encompass the old theory, on its ability to fix what the old theory wasn't quite measuring up at, but also on making new predictions. These three things are kind of the gold standard of new theories. So what happens with classical mechanics? Well, if you're like me, maybe you thought, when you were learning in high school, or maybe you think this now, that once you arrive at, a higher level of physics, you simply stop doing classical mechanics calculations, that, we've thrown classical mechanics out the window, and if I want to calculate a rolling bowling ball, I am definitely going to whip out the quantum mechanics to do that. And that is certainly not true. Theories that are good stick around. And the picture I want you to have in your mind is of kind of a larger theory encompassing a smaller theory, which was the one that we used before. And since this classical mechanics covers a lot of space, and it is intuitive, and the calculations are good, so when we can use classical mechanics to do calculations, we do. I use classical mechanics in my exam for my qualifying examination. It's still very much a theory that's alive. So we haven't thrown out an old theory. We've just modified it and looked for the spaces, looked for the boundaries in which the old theory doesn't cut it, and the new theory has to be brought in. So, this take-home picture, we have a modification to a theory at a different scale with experimental support. That part is key. Scientists aren't, really lining up to throw the old theories out the window. And the long-standing theory with a lot of experimental support still ends up being used. So coming back to the Hubble tension, the current cosmological standard model, our Big Bang theory, as you've heard it, is known as lambda CDM. That stands for cosmological constant. We use the symbol lambda to represent the cosmological constant, and CDM for cold dark matter. So this is a Big Bang theory, one of many Big Bang theories, but specifically it's the Big Bang theory that is kind of the most popular and well-supported theory we've got. And lambda CDM has a lot of success stories experimentally. It's good at, it predicted the cosmic microwave background, the distribution of chemical elements, gravitational lensing, positions of galaxies. There's a bunch more evidence. So, if we have somebody who's proposing new physics, who wants to use new physics to solve the Hubble tension, who believes the Hubble tension is an indicator that we need to change our theory, their new theory must not be incompatible with any of the old evidence and experiments. And in addition, the new theory must have independent and testable new predictions. If you want someone to believe, to support your new theory, you need to give an experiment that is different from what lambda CDM would say, that supports your new theory. Some additional skepticisms I want to highlight that will make it more difficult for a new theory to gain traction. So when scientists say a new theory is highly tuned, this basically means parts of the theory must be very specific numbers in order to work with the old evidence, and any theory that makes us special. So I mean, a great example of this is if you look at the motion of the sun, you could say, the sun moves in the sky because it is orbiting the Earth. We are at the center of our solar system. Same with the movement of the planets. And there's ways of solving the Hubble tension that make us special. But scientists tend to be skeptical of any modification to theory that makes us special, just because historically those theories have not ended up being correct. Putting us at a special place in the universe generally ends up not working out for us in the long run. So it could work. It could work well, and it might even be the actual case that we are in a special position, but they're going to be asking you for a lot more independent and testable new predictions in order to be convinced that we are somehow in a special place in the universe. So Theorist's goal is to make a new standard model that affects the Hubble constant measurement and has new predictions, and it will kind of encompass the predictions of lambda CDM, this cosmological constant cold dark matter Big Bang theory. So now we've got, this nice three-camp picture, both camps of which are working on a better understanding of systematics, a better assessment of uncertainty, and really, generating some really great new science here. And then over here, new physics, they're generating new ideas for how the universe works in the small details. So this can lead to new mathematics, and they're definitely proposing creative new experiments that will either lend support to lambda CDM as a theory, or maybe will send us heading off in a slightly different direction. And of course, as is shown in that graph I showed previously, there's people making different measurements of the Hubble constant in an effort to find out, where this tension might be coming from. Always making new measurements. So all of this is what science is. And this is basically what I wanted to say for my talk. Really talk about how, despite the idea that these camps are in struggle, despite the idea that someone here might be doing something that at first glance looks wrong, it's actually, all of this discussion is going to contribute in really, really interesting ways to science. I want to leave you with this graph, especially if there are questions about this. I'd be really happy to take questions about any of this talk, especially, and especially on how to read this graph. Thank you so much for tuning in.
Okay, thank you very much, Emily. That was really wonderful. Lots of discussion in the chat room there. I think a lot of people enjoying this and learning more about the universe. We do have some questions. I'm going to encourage anyone who has more questions to feel free to chat them, send them to us there, and I'll pass them along to Emily. We're going to go back to the beginning and start, and we have Mohammed Shaban, who asks, what is the difference between a theoretical scientist and an experimental scientist? Is one type more prone to disagreement?
That's a great question. So, I mean, the difference between a theoretical scientist and an experimental scientist can be a little, murky. Some definitely theoreticians these days are expected to propose experiments, but for the most part, theoreticians, come up with ideas for how the universe works and propose experiments, which are done by experimental physicists. And experimental physicists do themselves propose experiments. Many experimental physicists are very knowledgeable about theory. Is one more prone to disagreement than the other? I would say I'm a little bit young in the field. I wouldn't say I have a strong feeling for whether theorists or experimentalists disagree more often. It is certainly a division that you see in physics discussed sometimes. I'm just going back to the start of, yeah.
Wonderful, thank you. Yeah, I think physicists in general like to disagree. It's a sort of a sport.
Yes, Yes.
So Ransky asks a cosmological question. So the question was, my parents always ask me, if the universe is expanding, what is it expanding into? There must be something outside for it to expand into. I've tried and failed many times to explain this, but maybe you can.
Wow. Yeah, that's more of a philosophical question. I'm sorry to say I don't know that I have a better answer than that. I mean, the way I personally think about it is, the space itself is expanding, but the question of, what's outside of that space isn't one that concerns kind of my daily research, often. If it's not something that I personally can measure, it's not something that I personally can comment on, I would say. And I think, I think many scientists would, be due to remember that if it's not something that we can measure, maybe we shouldn't comment on it as scientists. I'm sorry if that, answer is unsatisfying to you, but maybe Michael has a few things to say about it as well, if you want to add to the discussion.
I would just say, if you're interested in that question, go back and watch the Misconceptions about the Big Bang
Great
talk,
talk.
where we get into that a little bit. But I agree with your answer. It's hard to say about a lot of these things. So somebody else, they're debating your assertion that your error bars are UFOs. They insist that they are, in fact, TIE fighters from Star Wars.
That's adorable. I love that. Yes, they are
fair.
TIE fighters also.
And I'm not sure, do we have any other actual questions here? So someone is suggesting an Isaac Asimov essay called The Relativity of Wrong,
Okay.
which I have not myself read, but it's about, apparently about pro-science and anti-science movements, which sounds really interesting, but I haven't read
That does
that
sound
myself.
interesting.
But I'm not sure, I don't see any other questions in the chat window. Any last things people want to ask? Just give people another minute in case anyone's typing something out there.
Sounds good. Yeah, back to talking about error bars or uncertainty bars. I'm trying to be particular about saying uncertainty bars, but sometimes you will hear them referred to as error bars. It was in my first year of undergraduate, we were for our experimental physics lab, which was excellent, by the way. It was done by Dr. Natasha Holmes, who's now a professor at Cornell, and she just, made a very revolutionary physics lab. But the first thing they had us do was write this diagnostic test where they had a bunch of these graphs with, these TIE fighter graphs, these little satellites, and I just absolutely baffled by them. I had no idea what they were on about. And now I think, they're the cat's pajamas. Uncertainty is great, and many physicists will speak, highly about it. It's also a headache insofar as it's hard to calculate, but you love it the way an artist loves drawing hands.
Indeed. So we have a bunch more questions coming in now. So I apologize if I mispronounce anyone's name, but Tabasam maybe says, did you enter your PhD directly after undergrad?
I did, actually. I entered it through the direct entry PhD program at U of T, which means I have 3 years left in my degree now that I've gone through the first 2 years. So you do 2 years, you do your qualifier and you propose what your thesis is going to be about, and then 3 more years of writing papers and writing your thesis, and then you get to defend, hopefully.
And it can be different at other schools. So this
Absolutely.
is, if someone is interested in pursuing a degree and you're sort of intimidated by jumping directly into a PhD, there are other routes you can go. You can do a master's first. Yeah. So this question, I think, is in 2 parts. It says, might be a dumb question. There are no dumb questions. But on the time versus Hubble constant graph, is the early universe depicted on the right-hand side with time increasing to the left?
I guess it is, yeah. That's a good point. I think if I had, done this graph differently, I would have put, oh no. I know why I did this. So this kind of goes back to the way cosmologists talk about time is to talk about redshift. And so redshift, goes from 0 at the now to, large numbers, 100, et cetera, at the early universe. So I made this graph as a cosmologist, but perhaps as somebody who is a little bit more in touch with the immediate reality rather than the early universe history, I should have swapped those around. But yeah, yes, the arrow should actually point in the opposite direction in terms of increase if I were to draw this graph like strictly correctly.
Okay, so some more, here's an interesting technical question, or not terribly technical, but so I think Earl asks, if the universe is expanding, does that mean that our rulers are expanding at the same rate, and so we might not notice the expansion happening locally?
So space is expanding, but objects are not expanding with the space. And that's kind of a weird key point, especially about inflation. So we talk about, the speed limit on the universe, which is, the speed of light, and, things expanding really, really quickly, faster than the speed of light. And that is because, that expansion applies to space. Yeah, I think that's sort of what I would say on that topic.
Okay, so this is definitely a more challenging question. How do we know that the Hubble constant is indeed constant?
That's really the tricky part here that I was trying to get at with this comment here. So the Hubble constant being indeed constant. So this is a tricky question because the answer, unfortunately, is that in lambda CDM, it is a constant essentially by definition. So if you want to ask the question, what if the Hubble constant is not a constant? You're actually asking, I would like a different theory. I would like to change it. So the Hubble constant right now is just the value of the Hubble expansion parameter, which is the rate of change of the scale factor of the universe divided by the scale factor of the universe squared. And that value at a specific time, which is now. So by definition, by construction in our current theory, the Hubble constant is a constant. But the deeper question is, this thing that we're measuring that we think is a constant, could it be more complicated than that? So if you want to, write some paradigm shifting theories about that go beyond lambda CDM, maybe talking about the Hubble constant isn't something that we will do anymore. But yeah, I mean that is a deeper and more complicated question, and the actual answer is unsatisfying. But the kind of implications of it not being constant, meaning that we need to look for new theories, potentially look for new theories, and that's something that a lot of us find very exciting.
Yeah, I think it's sort of ironic that we often say that, physicists like things to be simple, and yet one of our most favorite things is the question you just asked, could it be more complicated?
That's so true. That's so true. I mean, we love it when things are simple. But finding something new is also very exciting. It's exciting to see that the puzzle isn't quite solved yet, and every time we think we're close to cracking whatever puzzle that we've got, it turns out to have some more tricks for us.
Great. So here's another one. This is from Robert. It says, the necessity of the idea of dark matter, I understand, but not dark energy. Wasn't this introduced to address Hubble constant issues?
So dark energy, I would definitely say, I want to forward you to a different talk, which was done by Dr. Renee Holchek a couple, segments ago, and that goes into detail about dark energy. It's not really my area of research, but that talk is really quite good. So I definitely recommend checking that out.
Okay, and then one last thing that it's not quite a question, it's more of a comment, but you may want to comment on it.
Okay.
This is from Francois, who said, I thought the lambda CDM model postulates an infinite universe, and therefore the expansion is just that the overall density is decreasing, not that anything is expanding into space that didn't exist yet. It's a comment, but.
Okay, I guess I'm not sure I see a problem with that sort of, I'm not sure if I have philosophical disagreement with that comment or not. It's again, I could blithely say, is there a difference measurement-wise between those two concepts that you've said to me? And if there's not a different measurement-wise, I'm not going to say anything in my capacity as a physicist anyways.
Okay, wonderful. Well, I think that's the end of the questions. So I hope everyone has had a great time tonight. I'd like to thank Emily very much for taking the time to share her expertise with us. And I hope everyone has had a great time, and you will come back again. If you're interested in more Cosmos from Your Couch talks, please follow the Dunlap Institute on social media. We're on Facebook and Twitter and Instagram. You can also subscribe to us here on YouTube. And we'll be presenting these talks for the indefinite future, but certainly as long as people are in quarantine or in lockdowns and looking for a little bit of a way to reach out to the wider universe. Thanks, everybody. Have a great night
Bye.
or day.